This is a demo of embedded Swift, the same Swift that we used to write iOS and macOS apps. I was surprised at just how much cool stuff can be built on a chip which costs very little. Here are a couple of examples of a game that I made with just the screen, accelerometer, and the XIAO ESP32 chip. Quick note first, this video is sponsored by Seeed XIAO, who sent me this kit. The links in the description are affiliate links, and all the code in the demo will be open source on GitHub, so feel free to grab it and iterate on it. Now back to the demo. This is everything. We have the XIAO ESP chip, the shield, the OLED screen, and the accelerometer, plus a couple of connecting wires. To be honest, the hardware part was the easy thing to do. It was much easier than the software. The first item we can look at in detail is the shield. It's what connects all the pieces together, and it has a plug-and-play design. All of these ports can be used to connect various accessories to the chip. The Seeed XIAO has a sizable library of components you can look at. For now, we'll keep it simple and only connect the chip, the screen, and the accelerometer. The chip is tiny. It has a USB-C port for connecting to your computer, a couple of buttons, and 14 pins. You snap it into the shield and press firmly until you feel it secure. Next, we'll connect the display into one of the 8 ports. You can find one of the bottom left. Look for the one that says SCL. So we're going to plug in the accelerometer at the other SCL port. Same way, just snap in the cable and you're good to go. That's it. No need for soldering or any other difficult things to do. It's just plug and play and you're good to go at this point. The hardware is basically done. So once you've completed this step, you can move on to the software part. So quick bit of context, the official way to program these ESP chips is a thing called ESP-IDF. That's Espressive's IoT development framework. Espressive being the company that makes the chip. And basically it's the whole official toolkit. It's the compiler, all the drivers for talking to the hardware, the build system, and everything else. It's all written around C, and it's what everything here is built on top of. So when you see these functions, these types, that's the framework, that's IDF, and that's what we'll be calling from Swift. So just to talk through what's going on here, to talk to the accelerometer, we go over something called I2C. It's just a little 2-wire bus that lets the chip talk to the parts you plug in. And to set that up in C, we've got this config struct here that we fill by hand. The pins, the clock speed, the port number, then we create the bus and we get back this handle. This opaque thing we have to hold on to and pass around everywhere. And then every single call can fail. So you'll see this pattern over and over. Do a thing, get back an error code, check the error code, and if it's bad, bail out. It's all these manual checks, line after line. We've got raw pointers, we've got byte arrays. I have to size myself, and we're poking at registers by their hex address. And look, it works. There's nothing wrong with it, but honestly, it's a pain to write. It's easy to get wrong, and it's just not the kind of code I want to spend a whole project staring at. So the first thing I did is wrap it in Swift. And here's the wrapper. Same chip, same bus, but now it's a Swift type. We call it I2C bus. And look how it reads now. It's set up, we just give it 2 pins, the data line and the clock line, and that's it. All that config struct stuff, all the handles, all the error checking from before, it's all still happening. It's just moved in here, behind the type where I don't have to look at it every time. So from the outside, talking to the bus is now a one-liner, and reading and writing bytes is just a method call. It's the exact same hardware underneath, but it suddenly reads like Swift that I'm used to. And honestly, straight away, this just feels a lot more comfortable. The next bit is where we get really interesting. It got really interesting for me, because this is where embedded Swift is generally a bit more different from Swift, the Swift that I write every day. So here, I want to read a few bytes back from a register. Normally, on iOS, I wouldn't even think about this. I just make an array, read the bytes into it, and then move on. The system handles all the memory for me. But this chip has no heap, and that's a big deal. There's no malloc, there's no garbage collector, there's literally nowhere to grow an array at runtime. So I can't just casually allocate one whenever I feel like it. So instead, you'll see we declare the buffer up front, a fixed size, and that size is decided at compile time. And it sounds like a small thing, but once that clicked for me, it's actually changed how I write pretty much every line after it. You start thinking about memory in that way. Honestly, as an app developer, I just never really had to do that before. And now that we've got this nice clean bus to build on, we can do the same thing for the other two actual parts, the accelerometer and the screen. So first, the accelerometer. This is the chip that tells us which way we're being tilted. We wake it up and then we get a reading. We just ask the bus for 6 bytes, 2 each for X, Y, and Z. Then we stitch those bytes together into a proper numbers and hand them back as a simple little tuple. So from the rest of the program's point of view, getting the tilt is now just one call, sensor.read, and we get X, Y, and Z back. It's very nice. Then the screen. This is an OLED display, and the way these work is you've got a buffer in memory, 1 bit per pixel, and you draw into that buffer and then push the whole thing out to the display in one go. So we've got to fill it, clear it, we've got methods to draw into it, and then present, to actively send it to the screen. The thing that I want to point out is all of the genuinely horrible stuff, all of the datasheet bytes and magic numbers and init sequences, it all lives in these files that I basically wrote once and now never have to look at again. So everything that's left, the stuff that I actually work on day to day, just reads like normal clean Swift. It's really nice. Then, once all of those pieces exist, the whole program, the actual thing that brings it all together, it's just this. We set up the bus, we set up the sensor, we set up the screen, 3 lines, and then we drop into a loop that just runs forever. And in that loop, we read the tilt of the sensor, we smooth it out a little, and we work out where the bird should be. We draw it, and we push it to the screen. And then we do it again and again, 30-odd times per second. And that's the whole thing. If you've ever written an iOS app and you can read every single line of this, there's nothing exotic going on. And that's genuinely the part I like the most, that it ended up being this readable. The one line I do want to call out is this one. It's the low pass filter. It's a tiny bit of smoothing. Without it, the raw readings are jittery and the bird kind of twitches around. Without it, the motion goes nice and smooth. So now the moment of truth, we flash it onto the chip. This builds all of the Swift down into something the chip can actually run and pushes it over the USB cable onto the board. And then it boots. You can see it come up here in the console. It starts up, it finds the bus, it finds the sensor, and it starts reading. And these are real numbers coming off of real gravity in real time. If I tilt the board, the numbers move. There's no phone here, and there's no operating system underneath it. It's just our Swift running directly on the chip, talking to the hardware. And there we go. Swift running on a chip the size of a coin, reacting to me tilting it, and that's about 8 lines of code in total. What I keep thinking about isn't really whether this works. It clearly does. It's what people will build once iOS engineers realize they can write code that runs on outside of the iPhone. Next time I want to get this talking to an actual iPhone over Bluetooth, both sides will be written in Swift. And as I said, all the code will be on GitHub and the links will be in the description. And if you want to see where this goes, make sure to click subscribe and come back for more later.